Hello and welcome. In this video, I am going to explain to you exactly why RSA works and give you a full proof of correctness that doesn't require you to have any prior knowledge of number theory. When studying computer science, I learned about RSA in my computer security course. We looked at how RSA works, and we even did a few encryptions and decryptions by hand. But we never really learned why it works. So when I went online to find an answer to this question, of course I found a lot of proofs for the correctness of RSA. But these proofs usually relied on other results from number theory, and therefore they didn't really answer the question for me. So in this video, we will prove the correctness of RSA from scratch without relying on any prior knowledge. I assume that you at least know what RSA is, so I will only give you a short recap of how RSA encryption works. Next, I will give you a crash course on modular arithmetic, and then I will walk you through 3 key theorems from number theory we will need in order to prove RSA: Bezout's identity, Euclid's lemma, and lastly, Fermat's little theorem. I will give proofs for all 3 of these, but if you're not interested, of course, you can always skip them and go to the next section. And finally, I will show you why any message encrypted using an RSA public key can be decrypted using the respective private key. I will use Fermat's little theorem in order to do that. A quick disclaimer, I won't talk about how you actually implement RSA. So topics like the extended Euclidean algorithm or the square and multiply method for fast exponentiation are not part of this video, but I might cover them in a future video if you're interested. Also, I will try to explain every step as clearly as I can, but the things we are doing are not trivial, and also the individual sections all build on each other. So if at any point you feel lost, feel free to play parts of the video again or to revisit previous sections. So how does RSA encryption work? In order to create an RSA key pair, the first thing we need are 2 large prime numbers, P and Q. Primes are numbers that are only divisible by 1 and themselves. And in fact, they have to be distinct, so P can't equal Q. And I won't explain how exactly one finds such large primes. The only thing you need to know is that it can be done. It's not that difficult computationally. Then I calculate n, and n is simply the product of these 2 primes. And I also need to calculate phi of n. This is the so-called Euler phi function. You don't need to know what this means for our purposes. It's enough to know that this equals p minus 1 times q minus 1. And then we need 2 exponents, one public exponent for encryption and one private exponent for decryption. And the encryption exponent can be chosen basically arbitrarily. Usually we say that it's between 1 and phi of n. But there's one very important condition, the GCD, the greatest common divisor of E and phi of n. This needs to be equal to 1. So in other words, these 2 numbers, E and phi of n, they can't share any factors. And then I calculate the corresponding private exponent D. And D is simply the number that solves this equation. So E times D should be congruent to 1 modulo phi of n. Or in other words, E times D, if we divide that by phi of n, we will get 1 as the remainder. This equation definitely has a solution, so there is a D, and it has to do with this condition. And we will see why that is the case later. In order to actually solve this equation for D, you need what's called the extended Euclidean algorithm, but as I said, this will not be part of this video. At this point, we can finally create our key pair, which consists of a public key, which is the number n and the number e, and a private key, which consists of the number d. So the public key can be published and anybody can use it to encrypt messages, but you can't use it to decrypt messages. If you want to decrypt messages, you need the private key. So the private key needs to be kept secret. You might be wondering, well, we just calculated D like this. Couldn't an attacker simply calculate D the way we did? Well, they could if they knew phi of n. but we didn't actually publish phi of n, we only published n. So in order to figure out phi of n, you do this simple multiplication, which uses p and q. And there lies the problem. An attacker needs to know p and q, which two large primes were used to get to n. And finding large prime factors of a number turns out to be very, very difficult. You might say, okay, but maybe there's a different way of getting to this d. Well, there might be, but if you know d, there is a relatively simple algorithm that you can use to also figure out p and q. So finding d seems to be just as difficult as finding p and q. And this is the reason why experts believe RSA to be a very secure crypto system, because this prime factorization problem is notoriously hard to solve. The only thing that's missing, how do we actually perform encryption and decryption? That turns out to be surprisingly simple. Let's say we have some message m, and we represent that message as a number between 0 and n. So to encrypt that, we take it to the eth power, modulo n, and this gives us our ciphertext, our encrypted message. And in order to decrypt the ciphertext, we just take it to the eth power, again, modulo n of course, and this gives us our original message. And this is basically the really surprising thing about RSA, that you can't figure out what d is given e, but somehow these numbers share this magical relationship that using one number, d, undoes the operation when using the other number, e. And in fact, it turns out you can actually do the opposite as well. So you can also encrypt using d and decrypt using e. That also works. And this is, in a nutshell, the RSA crypto system. Of course, I've skipped a couple of details. For example, you can't choose any primes. Certain conditions have to be fulfilled, otherwise your key will be broken very easily. Also, you can't use any message m. You need to use what's called a padding scheme, again, to prevent certain attacks. But all these details won't bother us. In this video, we're only interested in this last step. Why are encryption and decryption, why do they undo each other? This is what we're trying to figure out in the next sections. But first, let's quickly talk about modular arithmetic. For RSA, we often have to do certain computations modulo some number. So for example, modulo n or modulo phi of n. And what this means is that we don't actually care about what the result is of our computation. We only care about the remainder after a division by, for example, n or phi of n. So let's say we do some calculation modulo n. What are the possible results? The only results that are possible are 0, 1, 2, and so on, up to n minus 1. So the result n, for example, is not possible because a remainder of n would simply be a remainder of 0. Notice that these numbers are all integers, meaning whole numbers. In fact, throughout the rest of the video, we will only be talking about integers. So every number you're going to see will be an integer. Let's look at a simple example. Let's say I want to add the numbers 8, 7, and 6, but I want to do that modulo 9. So 8 plus 7 plus 6 is 21. 21 divided by 9 gives us 2, because 2 times 9 is 18. And we have a remainder of 3, so the result is 3. For RSA, we also need modular multiplication. So let's say I want to multiply the numbers 8, 7, and 6, again modulo 9. And at first, this might seem a little difficult because you probably don't know what this product is off the top of your head. But there is a quite neat trick you can do. Basically, 8 times 7, this is 56, and 56 is 2 more than 54, which is a multiple of 9. So 8 times 7 is just 2 modulo 9. So we can just replace that by 2. So we can say this is 2 times 6 modulo 9, which is 12 modulo 9, and this also happens to be 3. But why does this trick work? Well, let's say I want to multiply two numbers a and b modulo some number n. And I know that a can be divided by n, and this will give me some remainder r. So I can write a as some quotient q times n plus some remainder r. And r, again, is some number between 0 and n minus 1. And we can plug that into our original equation. So we can say this is just q times n plus r times b. And if we multiply that out, we get b qn plus rb. And this is a multiple of n. So modulo n, this part here doesn't change the result at all because it's simply a multiple of n. It won't change the remainder. So the only thing that decides what the result will be modulo n is this part here. Only the remainder of a actually matters. So the key takeaway here is that if we do any calculation modulo some number, n for example, we can at any point replace an intermediate result with the remainder modulo that number n without actually changing the overall result. And it turns out this is absolutely essential because, for example, when we encrypt a message, remember that we just take the message to the eth power modulo n, but this will give us some enormous number. It will be absolutely huge, and there is no way we can actually store this number. So in order to calculate this, we need to replace intermediate results by the remainders, otherwise we will never be able to calculate that number. Another implication of the fact that we can always replace a number with its remainder, modulo n, is that we can multiply equations on both sides by the same number without changing the equality. Because if the remainder is the same, then the actual numbers a and b don't matter because, again, we get some multiples of n that cancel out in the modulo operation. We talked about modular multiplication, but what about modular division? Suppose I want to divide the number 7 by 2 modulo 9, for example. What I cannot do, I can't say this is equal to 3.5 because remember, we only allow whole numbers from 0 to 8 in modular arithmetic modulo 9. But is there a different way we can do this? Well, what is division by 2? It's simply multiplication by 1/2. And what is 1/2? It's the number with the following property: 1/2 times 2 is equal to 1. And we say that 1/2 is the multiplicative inverse of 2. So is there any number modulo 9 that has the same property? And it turns out there is, and this number is 5, because 5 times 2 is 10, and 10 is equal to 1 modulo 9. So 5 is the multiplicative inverse of 2 modulo 9. And in order to divide by 2, we simply multiply by the multiplicative inverse. We don't actually write 1/2 for that. We write 2 to the negative 1 to clarify that we're not actually talking about the fraction 1/2. And 2 to the negative 1 is 5. And 7 times 5 is 35, and 35 modulo 9 is 8. And this actually makes sense because 8 times 2 is 16, 16 modulo 9 is 7, and that's the number we started with, right? We divided 7 by 2, and then we multiplied it by 2, and we got 7. So this is exactly what we would expect. And we can generalize this if we multiply some number a times some number b, and then again times the multiplicative inverse of b, modulo n, then b times its multiplicative inverse is 1 by definition. So this entire thing is just a, modulo n. So now let's take a look at all the multiplicative inverses modulo 9. We already know the inverse of 2, it's 5. What about 1? The inverse of 1 is just 1 because 1 times 1 is 1. But what about 0? Well, no matter what number we multiply with 0, we will always get 0 modulo 9. So there actually is no multiplicative inverse of 0. And the same actually goes for 3 and 6 as well. There simply are no multiplicative inverses. If we multiply 3 by any number, we will never get 1 modulo 9. Same with 6. If we look at the multiples of 6, for example, we can see why. After 6 times 3 equals 0, the multiples simply repeat. We again get 6, 3, the next one would be 0, and so on. There is simply no multiple that is 1. So what do 0, 3, and 6 have in common? They're the only numbers among these 9 that share a factor with 9. All the other numbers don't have any common factors with 9. The way we can specify this is by looking at the GCD, the greatest common divisor. So for example, the greatest common divisor of 6 and 9 is 3, because 3 divides both 6 and 9, but no number larger than 3 divides both 6 and 9. The greatest common divisor of, for example, 0 and 9 is 9, because 9 is obviously divisible by 9. And 0 is also divisible by 9, because if we divide 0 by 9, we don't get anything left over. However, the greatest common divisor of 4 and 9, for example, is 1. There is no other number except 1 that divides both 4 and 9. It turns out the greatest common divisor of any two numbers is always at least 1, because 1 divides any number. I claim that in general, for any number a modulo b, a has a multiplicative inverse, or in other words, there exists a number x such that a times x is congruent to 1 modulo b, if and only if the greatest common divisor of a and b is equal to 1. Why is that? Well, a times x has a remainder of 1 if we divide it by b, which means that a times x is 1 more than some multiple of b, right? And we can subtract kb from both sides of this equation. This gives us a times x minus kb is equal to 1. And I rewrite this as a times x plus b times y equals 1, with y being minus k. So we have a, we multiply this by some number, and we multiply b by some number. We add them together, and this gives us 1. And we call something like this a linear combination of a and b. So the question is 1 a linear combination of a and b? And one thing that can help us answer this question is what's called Bézout's identity. And it states that the smallest positive linear combination of any two integers a and b is just the greatest common divisor of a and b. So how does this help us exactly? Well, let's assume that the greatest common divisor of a and b is 1. Then, according to Bézout's identity, 1 is a linear combination of a and b because it's the smallest positive linear combination. So this equation here has a solution for x. On the other hand, if the greatest common divisor of a and b is not 1, then it has to be a number greater than 1, because remember, the greatest common divisor is always at least 1. Let's say it's 2, for example. Now, 2 is the smallest positive linear combination of a and b. So 1 cannot be a linear combination of a and b, because it's smaller than 2. And the same goes for all other possible greatest common divisors greater than 1. Therefore, assuming Bézout's identity is true, this equation only has a solution for x if the greatest common divisor of a and b is 1, which means that this equation only has a solution for x if the greatest common divisor of a and b is 1, which means that a multiplicative inverse of a only exists if the greatest common divisor of a and b is 1. And this is exactly what we wanted to show. So let's prove Bézout's identity. I call the smallest positive linear combination of a and b S, and I want to show that S is equal to the GCD of a and b. And I'm going to do that in 2 steps. First, I'm going to show that S is greater than or equal to the GCD of a and b, so it's at least the GCD. And then I'm going to show that S is at most the GCD, so smaller than or equal to the GCD of a and b. And of course, if both these conditions are fulfilled, S is indeed equal to the GCD of a and b. Let's start by showing the first inequality. S is a linear combination of a and b by definition. A and b, they're both divisible by the GCD, right? Because it's the greatest common divisor of both a and b. So we can write a as some multiple ka times the GCD of a and b. And we can write b as some multiple kb times the GCD of a and b. So this equation here becomes this equation. And now what we can do is we can factor out the GCD. So this gives us the GCD of a and b times ka times x plus kb times y. What does this tell us? Well, s is a positive number because it's a positive linear combination. The GCD is also always positive. So we multiply two numbers together to get a positive number. One of them is positive, so this second factor also has to be positive. And this means that s is a multiple of the GCD of a and b, which means that s is at least as big as the GCD of a and b, and this is exactly what we were trying to show. Now we know that s is greater or equal to the GCD of a and b, but we still need to show the second condition. And in order to do that, we will show that s divides both a and b, which means that s is a common divisor of a and b, and therefore s, of course, can't be bigger than the greatest common divisor of a and b. So s is at most the greatest common divisor of a and b. So let's show that s divides a. What we can always do, we can always divide a by s, but this might give us some remainder. So we can write a as some quotient times s plus some remainder r. And this remainder has to be between 0 and s minus 1. And we want to show that it actually has to be 0, because then a is a multiple of s. Now we solve this equation for r. So r is a minus q times s, and s is a linear combination, right? So we can write r as a minus q times some linear combination of a and b. And what we can do now, we can factor out a and b. So this is a times 1 minus qx plus b times minus qy. And what we see is that r is also a linear combination of a and b. But remember, r is actually smaller than s. It's some remainder after a division by s. But s is the smallest positive linear combination by definition. So r can't be positive, right? Otherwise, r would be the smallest positive linear combination, but s is. So r has to be 0 and therefore not positive. Okay, so if r is 0, then we can write a as q times s, and therefore a is a multiple of s, or in other words, s divides a. And simply by swapping a and b, we can also show that s divides b using exactly the same argument. So to summarize, s divides a, this line simply means divides, and s also divides b. So s is a common divisor of a and b, and therefore s cannot be bigger than the greatest common divisor of a and b. And now we're done. The smallest positive linear combination of a and b is indeed equal to the GCD of a and b. A quick reminder for why we did all this. Bezout's identity was the last missing puzzle piece in order to show that a multiplicative inverse of a, modulo b, only exists if the greatest common divisor of a and b is equal to 1. Maybe you recall that when choosing the public exponent e for an RSA key pair, we had the requirement that the GCD of e and phi of n is 1. And now you know why, because we then said we need a number d such that e times d is 1, modulo phi of n. And this is simply the multiplicative inverse of e. And we know that this only exists if exactly this condition holds. Now we know about modular multiplication and modular division. So next, let's take a look at another very essential result from number theory, Euclid's lemma. The lemma states the following. If we have some prime number p, and this prime divides a product of two integers, a times b, then either the prime divides a or it divides b. And we can show that this is true by doing a proof by contradiction. So for some prime number that divides the product a times b, we assume the opposite of what the lemma states, namely that p does not divide a, and it also doesn't divide b. And we will show that this leads to a contradiction. First, we ask ourselves, what is the greatest common divisor of p and a times b? Remember that p is a prime number, so p only has two divisors, 1 and p. And we know that p divides a times b, so the greatest common divisor of p and a times b is p. What about p and a, so the greatest common divisor of p and a? Well, it can't be p, right? Because p doesn't divide a, so it has to be 1. It's the only other divisor p has. And the same is also true for b, so the greatest common divisor of p and b is also 1. At this point, we can use Bezout's identity. Because the GCD of p and a is 1, we know that we can write 1 as a linear combination of p and a. And for the same reason, we can also write 1 as a linear combination of p and b. And of course, this y doesn't have to do anything with this y, so we will give them numbers to distinguish them. Now we simply multiply these two terms together. The product of these two terms is still 1, of course, because 1 times 1 is 1. And when we multiply out all the terms, this gives us the following. We can see that 3 of these 4 terms have p as a factor, so we can factor out p. And if we now also rewrite this last term as a times b times y1 times y2, we can see that we now have a linear combination of p and a times b. So 1 is actually a linear combination of p and a times b, but according to Bezout's identity, the smallest positive linear combination of p and a times b should be p. And this is a contradiction. So our original assumption that p doesn't divide a and p doesn't divide b must be false, and therefore the original lemma must be true. We need one last theorem before we can finally tackle RSA, namely Fermat's little theorem. It says that for some prime number p and some integer a to the p minus 1 is equal to 1 modulo p. There is one condition though. The GCD of p and a must be equal to 1. But if you remember the Euclid lemma proof I just showed you, this basically means that p can't divide a. First, let's look at an example. We set a to 3 and p to 5, so 5 is prime, and a doesn't share any factors with p, so that's good. Then the theorem says that 3 to the power of 5 minus 1, which is 4, should be equal to 1 modulo 5. And if we do the math, 3 to the 4th power is 81, and this is indeed 1 modulo 5. So let's also look at something seemingly unrelated, namely multiples of a, 1a, 2a, 3a, and so on, all modulo p. So in our case, this would be 1 times 3 modulo 5, which is 3, 2 times 3 modulo 5, which is 1, because 6 modulo 5 is 1, 3 times 3 is 9, which is 4 modulo 5, and 4 times 3 is 12, which is 2 modulo 5. And one thing you might notice is that these are simply the numbers from 1 through 4, just in a different order. The question is this a coincidence? And as you've probably already guessed, it's not. I claim that as long as we select a and p according to Fermat's little theorem, then the multiples 1a, 2a, 3a, and so on up to p minus 1a, of course all modulo p, just give you the numbers from 1 through p minus 1 just in a different order. So every number appears exactly once. Or in other words, they give you a permutation of these numbers. To understand why this is the case, I think it makes sense to look at all the possible ways this could go wrong. So all possible situations where we don't get a permutation of the numbers 1 up to p minus 1. We are looking at the multiples modulo p, so we won't get any values larger than p minus 1. But what could happen theoretically is that we get 0. So there could be some multiple k times a that equals 0 modulo p. Well, what we can do is we can multiply this equation by the multiplicative inverse of a, which exists because the GCD of p and a is 1. So we can say this is k times a to the minus 1, and this is 0 times a to the minus 1. So 0 times a to the minus 1 is just 0, and a times a to the minus 1 is simply 1. So this gives us k must be equal to 0 modulo p. But if we look at all the possible values for k, they're 1, 2, 3, and so on, up to p minus 1. But none of these values are equivalent to 0 modulo p. So the situation that we get 0 as a multiple of a actually cannot happen. Another way this could go wrong is if two multiples of a give us the same result. So there are two multiples, ka and k prime times a, that give you the same result modulo p. And we can do basically the same thing. We multiply this equation by a to the minus 1, and this cancels out with a. So we have just k on the left-hand side, and similarly we have k prime on the right-hand side, and we see that k and k prime therefore have to be equal modulo p. But again, if we look at all the possible multiples, we see that they're all different modulo p. So the only way that k can be equal to k prime is if they're actually the same multiple. So the situation where two multiples give us the same result also cannot happen. What do we know so far? These p minus 1 different multiples actually give p minus 1 different results because no two multiples are the same. And also we excluded 0, so all multiples give you results in the range of 1 up to p minus 1. So the only way this works is if every number from 1 up to p minus 1 is covered exactly once. And this is what we were trying to show. So now that we know that these multiples of a give a permutation of all the numbers from 1 up to p minus 1, we will do the following. We multiply them all together, and as we know that every number is covered exactly once, for example, this might be p minus 2, and this might be 3, and this might be 5, and so on, we know that the result of this product, modulo p, is simply the product of all these numbers, 1 up to p minus 1. We can also write it as p minus 1 factorial. This is just a shorthand notation for the same product. Then we move all the a's on the left-hand side to the left and simplify the rest again to p minus 1 factorial. And of course, we can also write the product of a's as a to the p minus 1. And now it's starting to look a lot like the thing we're trying to prove, right? We just need to multiply both sides by the multiplicative inverse of p minus 1 factorial. And we can do that as long as the GCD of p and p minus 1 factorial is 1. So let's check if that's actually the case. Remember, we are talking about a prime number, so the only way the GCD is not 1 is if the GCD is p, because the only divisors p has are 1 and p. And the only way that the GCD is p is if p minus 1 factorial is divisible by p. So let's verify that this is not the case. Let's assume that p did divide p minus 1 factorial. P minus 1 factorial can be written as p minus 1 times p minus 2 factorial. So we can apply Euclid's lemma, which says that this is only the case if p either divides p minus 1 or if p divides p minus 2 factorial. P obviously does not divide P minus 1 because P minus 1 is smaller than P. So P would need to divide P minus 2 factorial. But we can write P minus 2 factorial again as P minus 2 times P minus 3 factorial. And we can apply the exact same argument. So then P would need to divide either P minus 2 or P minus 3 factorial. But again, P minus 2 doesn't work. And if we keep going, basically we will see that none of these factors are divisible by P because they're all smaller than P, which means that our original assumption that P divides P minus 1 factorial must be false. And this means that the GCD of P and P minus 1 factorial can't be P, so it has to be equal to 1, and therefore P minus 1 factorial has a multiplicative inverse modulo P. This means that we can safely multiply this equation by the multiplicative inverse of P minus 1 factorial, which then cancels out with P minus 1 factorial, giving us 1. So the only thing that's remaining is a to the P minus 1 on the left-hand side and 1 on the right-hand side. And this is exactly Fermat's little theorem that we were trying to prove. We are finally back to where we started, but now equipped with the necessary knowledge to understand why RSA works. But before we do that, let's first get rid of everything we don't need. We want to show that any message m taken to the eth power and then taken to the dth power will give us back our original message. So let's plug m to the e into our second equation. And now we see that basically everything we're doing is we're multiplying m by itself, e times, and multiplying the result of that by itself another d times. So actually, we're just multiplying m by itself e times d times, which means that we can write this simply as m to the e times d. And by the way, this tells us that RSA also works the other way around, because this is the same as saying m to the de, which is the same as m to the d to the e. So it doesn't matter if we use e or d for encryption, as long as we use the other one for decryption. So let's show that this is actually true. I'm going to do this in 3 steps. First, I'm going to show that m equals m to the ed modulo p, not n. And similarly, I'm going to show that m also equals m to the ed modulo q. And as the final step, I'm going to show that if it holds for p and for q, then it must also hold for n, which remember is simply the product of p and q. Let's look at why it works modulo p. There are actually 2 cases we need to handle separately depending on the GCD of m and p. Remember that the GCD can only be p or 1 because p is prime and these are the only factors p has. Let's look at case 1 first. If the greatest common divisor of m and p is p, this means m is divisible by p. But if m is divisible by p, then m modulo p is just 0, right? Because there is no remainder. And remember, we can always replace intermediate results with their remainders. So m to the ed just becomes 0 to the ed. And this is, of course, equal to 0, because 0 multiplied by itself a bunch of times is still 0. So case 1 is already dealt with. Let's now focus on case 2. If we look at our exponent ed, this looks familiar, right? Because we've selected e and d to be multiplicative inverses modulo phi of n. Let's use this fact. If e times d modulo phi of n is 1, this simply means that e times d is 1 more than some multiple of phi of n. So m to the ed can be rewritten as m to the power of 1 plus k times phi of n. Let's now replace phi of n with the actual definition. This gives us 1 plus k times p minus 1 times q minus 1. And this is still equal to m modulo p. So we're taking some value m to some power that includes p minus 1, and then we take the result modulo p. This looks a lot like Fermat's little theorem, right? A quick reminder of what the theorem actually says. We can see that we can in fact apply this because our number p is prime, and the GCD of the message and r prime is 1. But of course, our equation doesn't exactly look like Fermat's little theorem. So let's try to modify it such that we can actually apply the theorem. The first thing we need is a 1 on the right-hand side, but this is actually easy to do because we can simply multiply the equation by the multiplicative inverse of m, which we know exists because the GCD of m and p is 1. On the right-hand side, this gives us 1, as expected. And on the left-hand side, we can make use of the fact that m to the power of 1 plus something is just m times m to the power of that something. Which means that we can write the left-hand side like this. And again, m times its multiplicative inverse is 1, which means on the left-hand side, we're just left with this. And now we're almost there. In order to get this into this form, we use one last trick, namely that we can first take m to the p minus 1th power, and then take it to the k times q minus 1th power, which looks like this. And now we can finally apply Fermat's little theorem, which tells us that m to the p minus 1 is 1 modulo p. Again, we can replace an intermediate result with its remainder. So we have 1 to some power is 1. And of course, this is true. It doesn't matter what the power is. If we multiply 1 by itself several times, we will always get 1. So in both cases, m to the ed is indeed equal to m modulo p. So we've shown that it is true modulo p, but is it also true modulo q? And of course it is, because we can simply apply exactly the same argument, just swapping p and q. So now that we have shown that it is true for both p and q, it's actually surprisingly easy to see that it also has to be true for n. If we divide m to the ed by p, we will get m as the remainder, which means that m to the ed is m more than some multiple of p. So m to the ed is m plus k times p for some k. But similarly, m to the ed is also m more than a multiple of q. So it's also m plus k prime times q. Let's focus on the right part of this equation. We can subtract m from both sides, which leaves us with some multiple of p, which is equal to some multiple of q. But if kp, whatever this number is a multiple of q, this means that it's divisible by q. So we can write q divides kp. And q is a prime number, which means that we can use Euclid's lemma again. So q either divides k or q divides p. Remember, p is also a prime number, and p is not equal to q because we've chosen them to be not equal. So this means q cannot divide p because p is only divisible by p and 1, and q is neither of them, so q can't divide p, which leaves us with q divides k. But if q divides k, this means that k is a multiple of q, meaning we can write k as, let's say, k hat times q. And we can plug this into our original equation, which gives us k hat times q times p. And now let's look at the left part of this equation. qp is just n, right? Because n is the product of p and q. So we can write qp as n. And now we can see that m to the ed is m more than some multiple of n. Or in other words, if we divide m to the ed by n, this leaves us with a remainder of m. And this means that m to the ed modulo n is m. And this is it. We have just proven that any message taken to the edth power gives us m modulo n. And this is why RSA works.